Welcome back to our video module on quantum mechanics. Today, I'm going to take a final step in exploring the ladder operators to give us a glimpse into how useful they can really be. I'd like to start off first by showing you a rough sketch of the various energy levels within the simple harmonic oscillator and what the wave functions may look like in this setup. And if you'd like something better than a sketch, I've also included a prettier model of first the ground state and then the first, second, and third excited states. One particular thing I'd like to note is this point right here, the point where the energy of the state is equal to the potential energy. This is our classical limits. In other words, you can imagine if we had a particle, in this well and it had the energy of the ground state, down here it'd be all kinetic. And when it gets right here, all the energy would have gone into potential and the particle would have turned around and gone back and forth. Now, obviously, because we're in the quantum domain, things don't quite work that way. It's interesting to point out that while the classical limit says a particle would have turned around right here, the quantum mechanics says there's still the possibility that a particle is out here in a region that isn't allowed in classical mechanics. But for now, I'm going to put that aside. And I'm going to offer you a simple problem. What is the expectation value of the potential energy of a wave function in a simple harmonic oscillator? Well, we know enough now that we can rewrite this as 1/2 m omega squared x squared, where x is the x operator, which we can simplify by getting x squared by itself. And we remember from our operators that we simply take the integral of the wave conjugate times the x squared operator times the wave itself. And of course, we know enough about using operators that we actually could write the integral form of how to find this expectation value. But there's two rubs to that. The first is look at the ground state. You're trying to do an x squared on a Gaussian, which is doable, but it's painful. Not nearly as painful, though, when you actually have to find subsequent psi of n's and put that into some sort of series form. So this is solvable, but it is not trivial. But what if we made a substitution? What if we made the substitution relevant to, but what if we made a substitution? What if we use the lowering and raising operators instead of the position operator? So first, we'd substitute our raising and lowering operator sum into wherever we see our x, and we notice that it has a square. Next, we'd go ahead and FOIL, do our term-by-term multiplication. We bring our coefficients out front. Now this is where it gets fun. Let's imagine right here that we're going to apply the lowering operator twice on c of n. Well, that's going to give us a c of n minus 2 times some coefficient. But c of n minus 2 is then going to get multiplied by c of n conjugate. Well, these are all orthonormal states, which means that c of n times anything other than c of n is going to be 0, which means this term right here will have no effect. Likewise, the raising operator times the raising operator is going to have 0 effect. The only terms left are going to be right here where we raise and then lower, and here where we lower and raise. We also know that the integral of Cn C equals 1. Using this information and using this information right here, we're able to quickly solve, and we end up with total energy divided by 2. So here we've been able to take a real headache of an integral, and by using raising and lower operators and some of this peculiar characteristics of orthonormal states, we're able to solve this in only a couple lines. It's worth noting that I pulled out this example because it ends up with an interesting fact that the expectation of the potential is the energy of the state divided by 2. Interestingly, a corollary to that is that if half the energy is going to the potential, that means the expectation of the kinetic energy is also half. So in summary, using raising and lowering operators, especially when we're looking at position and momentum operators, gives us another tool that can be remarkably powerful. and some of the problems we come up with in simple harmonic oscillators. I'll also note that if you don't want to use raising and lowering operators, or you're in the mood for doing full integrals, that Hermite polynomials are the path you want to take. Thank you for joining me in this exploration of the simple harmonic oscillator. I look forward to joining you next time when we look at even more interesting potential profiles. I'll see you then.